Okay, today's lesson, we're going to start chapter 5. I'd like you to begin with something that should refresh your memory just briefly about some things in today's lesson. So pause the presentation and let the students answer these warm-up questions, probably about 5 minutes. Okay, number 1, define and sketch the perpendicular bisector of a segment. Well, to define it, to explain it, a perpendicular bisector is a line, ray, or segment that intersects a segment at its midpoint and forms a 90-degree angle with it. So if I'm sketching one, let's put the segment this direction, and then a perpendicular bisector through it. That's not a very good estimate, but probably about there, right angle, a line going through it. Now realize the segment that's getting bisected doesn't have to be horizontal. So I could have drawn the segment this direction and made my line through it perpendicular bisector. I think we get to believing that the horizontal is always the one that gets bisected, and that's not always the case. Okay, number 2, define and sketch an angle bisector. An angle bisector is a ray that divides an angle into 2 congruent angles. So that picture might look like this. Mark those angles congruent. Maybe you started with an obtuse angle and you've got an angle bisector, something like that, dividing it. And number 3, find the midpoint and the slope of segment AB. The midpoint should have been -1/7 and the slope was +1/3. We are going to be writing the equation of a perpendicular bisector again today, and you'll need to calculate both of those correctly. Right, so each student should get a note packet for chapter 5. We're going to be talking about things on the first 2 pages. You are going to need construction tools, so if you don't have those, pause the presentation and have all the students get a packet of construction tools. All right, we're going to talk about angle bisectors, perpendicular bisectors, and then on the next page, medians and altitudes. There are a couple terms that we'll use. What does the term equidistant sound like it means? Usually students say equal distances. Well, that's true. That's exactly what it means. When a point is the same distance from 2 or more objects, the point is said to be equidistant from the objects. We will have theorems starting today. There are many in this chapter where a point is equidistant from something. And so you need to pay attention to what it's equidistant from in order to get these relationships in your mind. The first theorem and converse are called the perpendicular bisector theorem, and it's converse. So don't skip the wording. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So as students are drawing that hypothesis, what they are drawing is a segment AB, and then the line XY is the perpendicular bisector. Notice the markings on the diagram, students. It is the perpendicular bisector of that segment AB. Now the conclusion, it says then what's it talking about? It's talking about this point X that's on the perpendicular bisector. It is equidistant from the endpoints of the segment. So in the conclusion, notice it tells you that from X to A equals the same distance as X to B. Those two are they're equal. That point is equidistant. Now the converse, we've done converses. That means we're switching the order of the hypothesis and conclusion. So notice the conclusion, the conclusion from the first one is now the hypothesis. If XA equals XB, so that's what's marked in this hypothesis, XA's length and XB's length are the same. If that's what you know to begin with, then you can conclude that xy is perpendicular to AB and y is the midpoint. So in other words, you can conclude that line xy is the perpendicular bisector of segment AB. So the difference between those two is, do you start knowing it's a perpendicular bisector, or are you concluding that it is a perpendicular bisector? Again, pause this if I haven't given enough time for the students to write down what they need to. The term locus is a word that'll pop up a few times in our textbook. I don't use it myself too much, but to understand what our textbook is talking about, a locus is just a set of points that does something special, satisfies a certain condition. So that definition of a perpendicular bisector, you can say it's the locus of points in a plane, so the collection or set of points that are equidistant from the endpoints of the segment. Now, in order to get an idea better of what that's talking about, I need you to construct a perpendicular bisector. I really didn't give you a space on your notes, so maybe flip over the page, give yourself a segment, and then construct its perpendicular bisector. You can pause here. I will do some sketching on the construction before too long. Okay, so if anyone got stuck, the construction should look like, okay, here's a segment. You're going from one end and you're making an arc that is more than half the width of that segment. And then from the other end point, you'll do that same arc. You'll draw, I'm going to change colors, draw that segment. That is the perpendicular bisector. Students, you might notice that we did this construction for midpoint. We also used it for segment bisector. It actually gives a complete perpendicular bisector. Now, in order to understand what that locus of points was talking about, notice that any point that is the same distance to each endpoint, like that point that you constructed there, that point is on the perpendicular bisector. If you go lower, this point is equidistant each way. It's on the perpendicular bisector. The point down here that you constructed is the same distance to each side, to each segment end, I should say. And we could do the same for any point along here. If you would measure each direction, it's going to be the same both ways. So this collection of points that I'm making, all of these points are equidistant from the endpoints of the segment that you started with. That creates the perpendicular bisector. All right. So let's see if we can apply that theorem. Okay, as you look at this picture, notice you do have the right angle and the segments are marked equal. So P, N, that line is a perpendicular bisector. So now the theorem, look back at the wording. If you have a perpendicular bisector, a point that's on it, like N, it says N is equidistant from the endpoints of the segment. So if it's 20 or 2.6 to endpoint L, then it's going to be 2.6 to endpoint M. So the length of MN would be 2.6 also. On the next example, we still have a perpendicular bisector. This time I haven't given you just a number. I've given you expressions. Still, the idea is the equidistant. U is equidistant from T and from V. So this segment and this segment are the same. So your algebra expression or equation you should be writing. (3x plus 9) has to equal 7x minus 17. Solve the equation. And then I don't want to know what x is. Did you find TU for me yet? So do find x and then TU. Okay, so both of those we had a perpendicular bisector. Now in this problem we do not have a perpendicular bisector right now. We know that there's a 90 degree, but it didn't tell us that DB and DC are the same. So this one is actually using the converse. Notice that we do have a point, A, that is the same distance to B, it's 38 that way, and to C, it's also 38. So A is equidistant from the endpoints of a segment. So the converse says then it, A, is on the perpendicular bisector. So that tells us that BD and DC are equal because A is on the line that is the perpendicular bisector. It was already marked perpendicular, so we get the bisector part figured out. So what's the length of BC? DC and DB will be the same. So when you take that times 2, you get 24 for the length of BC. Right, this picture looks more complicated, but let's pick just parts of it. And notice in the directions it says DG, EG, and FG are all perpendicular bisectors of equilateral triangle ABC. We're supposed to find the length of GC. Okay, let me highlight. GC goes from points to there. I think the easiest one to think about would be the bottom part of this diagram. It said FG, switch colors, FG is a perpendicular bisector. So there's the perpendicular bisector. Think back to what that theorem said. G is a point that's on that perpendicular bisector, so it's equidistant from C and A. So GC and GA are going to be the same length. Well, that really didn't help me too much because I don't know what either one of those are. So let me think to a different part. Okay, let's go with DG being the perpendicular bisector. G is a point on that segment, or that line. So since G is on the DG perpendicular bisector, it's equidistant from the ends of that segment. So that's GA and GB. Those two will be the same. They told us that that was 13.4. So AG is 13.4, GC is 13.4, just like GB. So all of those are the same length. You might want to take a look at that picture a little bit closer to see what I highlighted. Okay, we've done this before. Let's write the equation for the perpendicular bisector of the segment that goes through those 2 points. Okay, in chapter 3, we did equations of lines. So we need the slope and we need the point that the perpendicular bisector has to go through. That's going to be the midpoint. Remember, the slope of AB and the slope of the one you're creating can't be the same. They have to be slopes that would indicate perpendiculars. They have to be opposite signed and reciprocal values. So pause this, have the students work on it for a while. Okay, what have you come up with? So the point you need to use is 1,4 and the slope of -3/2. There's my point slope equation, and I did convert it into slope-intercept. I really didn't say what form to put the equation in, so there's a couple answers you could have there. Okay, let's go to angle bisectors. And as we get into this one, we are going to make an angle bisector again. But I also need to remind you that the distance between a point and a line is the length of a perpendicular, because we're going to try and find the length of, or the distance from a point that's on the angle bisector to the side of the angle. We have to always make that a perpendicular to the side. Okay, it says we're going to make an angle bisector, place C on it, and then get the perpendiculars to each side. Okay. If you need to leave this up for a while for the students to do the activity. Okay, what should it look like, class? You should have had an angle to start with. I don't care how big it was, acute, obtuse, whatever. You constructed the angle bisector. All right, now, what I want you to do is pick a point on the angle bisector, and let's make a perpendicular to each side of the angle. So perpendicular, if you are constructing, you're going to go from C and cross the side twice. From those two intersection points, you'll create your X. That will make the perpendicular to this side. And then you'd have to do the same to the other. Looks like I might have to extend my ray there. Okay, so from C, cross that side twice, and from those intersections, make your X. And we'll get the distance to that side. Now, this is just a sketch, so it's not perfect. Hopefully your construction is better. But let's have you measure from C to this side. Measure how long that length is. So measure CD, and then measure CB. What did you find when you measured? They should have been the very same length. Because if that's an angle bisector, it has to be the same distance from each side to cut it in half. All right, what theorem does that relate to? It's called the angle bisector theorem. And the converse is here also. So you'll need to pause this so that they can get their diagrams done, but I will do some explanation also. Okay, that angle bisector theorem hypothesis. Notice that you do make an angle bisector. So you've got to mark that this angle is the same as this one. So that ray is an angle bisector. The point that's on it is the same distance, perpendicular to AC and perpendicular AB, or excuse me, CB. So AC and BC are the same length if that's an angle bisector. Now the second one is the converse. So your hypothesis picture, is it marked that it is an angle bisector? Notice it's not. There's no markings down by vertex P. So this one starts out, the converse is if a point in the interior of the angle is equidistant from the sides. So we know that this length AC and the length CB are the same as we start the converse. What do we come up with? Well, look at what angles they gave you in the conclusion. Those are the angles at vertex P. So basically, knowing that those are the same, we would know that ray PC is, let's see, I'll put bisects angle APB. So that is an angle bisector. Okay, so pay attention to whether you start with an angle bisector or conclude that there's an angle bisector. Again, that locus of points wording could be used to describe an angle bisector. Okay, an example. We're supposed to find the length of BC. As you analyze the diagram, do we have an angle bisector? We do. This angle and this angle are the same, so AC is an angle bisector. C is a point that's on it. Perpendicular to D is 7.2. So when you go perpendicular to B, what length would that be? You're right, it's 7.2. That point's equidistant from the ends, or from the sides of the angle, I should say. Okay, in this picture, they have some angle bisectors, but didn't mark the angles. So MP is an angle bisector, and then LP is also an angle bisector. I'm going to put some markings in the diagram. If MP is an angle bisector, these two are the same. And if LP is an angle bisector, these two are the same. So if that angle's 50, wouldn't angle QLP also be 50? I don't know if that helps us for anything, but notice that. Okay, find the distance from P to MN. So how far is P from side MN? They don't have a perpendicular drawn in there, do they? If you want to see one, I don't know, let's estimate. Is it maybe about there? So what's the length of that segment? Well, P is equidistant since it's on MP. MP is an angle bisector. P's the same distance if you go to the side MQ, or if you go to the P, we'll call it T. Sorry. So PQ and PT will be the same length. So how far is P from that side? 5 units, just like PQ is. I'll take off some of those markings so you can see again what that looked like to start with. So read the directions to figure out what it's telling you. Okay, here's one that's asking you, I guess it's the same picture that I just had, but it's asking you something different. Find the measure of angle PMN. I'm going to bring back some of the markings. It said this was an angle bisector, and then down here was an angle bisector, and this angle we said was 50 degrees. Okay, you're supposed to find the measure of angle PMN. So what's the measure of this angle right there with the dot? Okay, do some thinking. Okay, one thing you can do is look at the big triangle. What do the angles in a triangle have to total? It should be 180 degrees. Well, if this angle is 20, and then 50 and 50, this angle is a total of 100. What should this last top angle be? 180 minus 120 leaves 60 degrees. And then it's bisected. So the angle we're looking for, wouldn't that be 30? So I found the angle total based upon the whole triangle. Figured out what angle LMN is, and then took half of it. Okay, let's have you try. So pause so that they can think. Okay, distance from P to Q, or excuse me, distance from X to PQ is going to be the same as from X perpendicular to Y. How do I know that? Well, we've got some angle bisectors going on. Okay, so if I back up and give you one at a time, if this angle's bisected, then perpendicular xy and x this direction would be the same, 19.2 for both of those. And then if qx is an angle bisector, then from x that side or that way and x this way, those green ones would also be the same, 19.2 for both of those. 19.2, 19.2. That point is the same distance to every side of that triangle. We'll do some more with that idea on Monday. Okay, now you're trying to find the angle. I did one like this just a little bit ago. So pause the presentation and have the students figure out the missing angle. Did you use the great big triangle? Find what those angles are, and then you can bisect. Looks like the final answer should be 52 degrees. I'll look through my work if you got stuck. You found the big angles, 52, 24, and then subtracted to find this one, and take half of it. A simpler picture. Now this one doesn't tell me that the angle is bisected. So what should you notice in this one? Notice that point M is the same distance when you go perpendicular to L and when you go perpendicular to J. So M is equidistant from those two sides of the angle. So this is the converse. So the converse then says M is on the angle bisector. So your 2A plus 26 has to equal the 3A plus 20. Solve, substitute, 38 degrees. And one that's similar. (25 degrees). So the converse of the angle bisector theorem was used there. This one doesn't have the tick marks, but notice they said XW is 5.7, ZW is also 5.7. This looks kind of weird because it's an obtuse triangle. But W is equidistant from the sides of this angle. So that means that angle is bisected. And the angle, if WYZ is 63, you're going to take it times 2. To get the angle we're looking for. If you'll turn your page, the median is next. A median, it might sound like that has to do with the middle of something. Yeah, part of it is the middle of something. A median goes from a vertex to the midpoint of the side that's across from it in the triangle. Notice it couldn't connect to the midpoint of a side that's right beside it. So in your notes, you'll see a space for a construction of a median. I'd like you to grab the compass and straight edge, and let's do a construction. So make yourself, as best you can, just a scalene triangle of some kind. Try not to make it equilateral. All right, now how do we construct a median? We need to find the midpoint of a side. So I don't really care which side you use, just for your sample. I'm going to use the bottom. So I'm going to use these 2 points and do my construction from each end to find the midpoint. And then connect the midpoint to the vertex that's across the triangle. That red segment is a median. A segment whose endpoints are the vertex of the triangle and the midpoint of the opposite side. Now, as we work with these on Monday, we'll be putting all 3 medians in one triangle. If you have time, it would be fun for you to construct all 3 medians and see what happens. There's a special relationship that happens. So if this is a median, then if this is 15 inches, then wouldn't this be 15 inches also? Not a whole lot that we can do with one median. It gets more interesting when we put multiple medians in. Is the median the same thing as the angle bisector? You still have your sketch or your construction? I just got rid of mine. But if you've still got that construction where you've got your median, let's see, is that also an angle bisector? Well, grab your protractor. Measure the angle here and the angle here. Let's see if they are the same. After you've measured, what do you think? They typically are not the same. Now, there are certain triangles where they will be. If we have a certain isosceles triangle, if we're coming from a certain median in that isosceles triangle, they will be the same. And your equilateral triangles, there's a lot of these things, these segments I'm talking about today that end up the same. So median is not always the same as the angle bisector. So I'm going to answer the question no, that it really is not, unless it's a special situation. And the 4th thing to talk about today is what an altitude is. An altitude is a perpendicular segment from a vertex to the line containing the opposite side of the triangle. Now, what the heck does that mean? Well, you can't just say that it goes perpendicular to the side of the triangle, because depending upon what kind of triangle it is, you might not be able to do the perpendicular inside the triangle. Notice my pictures here. The red segment is the altitude. In the first triangle, the altitude, the perpendicular, it's going to stay right inside. Is it cutting that side in half? No, it's not. It just goes wherever it needs to go from this vertex and make a 90-degree angle. Now the second picture, and you've got a diagram kind of like that on your notes that you can sketch it in. If you go from this top vertex and try and make a 90-degree angle, if you would try and go in the triangle, notice that there's never a 90-degree angle. The 90-degree angle occurs when you are actually outside the triangle. So here's where the 90-degree happens. So I dashed that side to extend it so that you can visually see the 90-degree angle. Those are kind of the tricky ones. What kind of a triangle was that? It is obtuse. Not always is the altitude outside the triangle. It depends which vertex you're going from. We'll talk about that some more on Monday too. In this last triangle, if I go from this vertex and make a perpendicular, notice how it traced right on the side of the triangle. So what kind of a triangle is that one? It's got to be a right triangle for that to happen. And not every altitude in that one will be along the sides of the triangle. when we put all three in on Monday, we'll see the differences. Okay, so that's where they could be, and I made the easy ones in this diagram today, so I didn't make you turn the paper. But let's do the actual construction. So grab your compass and straight edge. And let's do a altitude. You want to do the easy triangle? Let's do an easy one and then an obtuse one. So let's make an acute triangle. Maybe looking about like this. And let's try and do the perpendicular, the altitude that goes from this vertex. So if you will just focus on that vertex and this side of the triangle, ignoring the rest of the triangle, it's just the perpendicular construction we've done previously. You might have to extend this side. I might run out of room on my sketching. But go from the point and cross that line twice. From where you crossed, make the X, same distance from each one, and connect the X to your vertex point. That would create your perpendicular. Now on an obtuse, I'll make it look like your nose. It was kind of like that. Again, if we go from this top point, we're going to have to extend this side of the triangle so that you can put the point of your compass on P and cross the line twice. You've got to have that extension to find where it crosses. Those two intersection points are what you use to make your X to create the altitude. All right, again, you might need to pause so that they can practice those constructions. Is the altitude the same as the perpendicular bisector? Now think about this last one you did. If you have an altitude that is out here, is that bisecting the side of the triangle? Not at all, because it's not even touching it. So a perpendicular bisector would be one that would be like going here. This would be your perpendicular bisector. The altitude is not the same. Again, in a certain triangle, it could be or would be the same, but in general, it is not. The altitude has to connect to a vertex of the triangle. The perpendicular bisector does not. Now you might notice that we did not have theorems about just medians and altitudes. When we do some more with them in triangles on Monday, we will have the theorems that apply. But today you need to just become familiar with what they are and be able to pick them out. Okay, I would like the groups to do these check of understandings. So we've worked with a turnaround buddy. So get together with your buddy. Pair up differently if there are some absences. And work these two problems. The sub will show you the answer, then give you the next screen, and so on. Let's check your understanding before you start on your assignment. Next set. Pause again. Give the answers. Be sure you're discussing them. Another problem. These problems, it's kind of a matter of seeing what's there and what do you apply to figure it out. And let's finish by writing an equation of the perpendicular bisector, again with your partner. And that solution is this one. Okay, I think you probably are running out of time today. What we're going to do on Monday then is put the 3 perpendicular bisectors on one triangle, and then the 3 angle bisectors, the 3 medians, and the altitudes. If you want to do some exploring, there's an app called Geometry Pad, or you could use the GeoGebra that we have worked on a little bit. You might put 1 perpendicular bisector and then move the triangle around and see how the perpendicular bisector moves in relation to it. Same thing with angle bisectors, medians, and altitudes. Wish I was there to have you explore that with me, but we'll do some more with it on Monday. Later.